Hello. Screen sharing's on, recording's on. Okay, good afternoon, everybody. So in the last class, we were talking about implementing behavior in a game using finite state machines. And so I showed you the gang of 4 state pattern in the last lecture, and we implemented a little state machine. Well, not a real state machine. We implemented the state pattern to model the turnstile problem that we were talking about in the previous class. Now, the problem with that example is for game development, that's not the most realistic way to solve this particular problem. So today I want to show you an example of how you can do this in the context of a video game. Okay. So for games, a general purpose state implementation might have the following methods instead. So remember the previous state machine that we implemented was very specific to a turnstile. If you want something that's reusable in a game, you have to design the interface for the state in a particular way. And so there's many different ways you can do this. This is just one of the common ways that you could do this. And so for the state pattern for a game, your state objects might have the following methods. So there could be an enter method. So the enter method is the method that's called when you first transition into the state. Right? And so typically the enter method is going to do whatever setup it needs to do for the state object. Right? So you can think of it as acting as a constructor for the state object. The do method represents the actions that are performed while the entity is in that particular state. The exit method is the method you call when you want to transition out of the state. So just before transitioning out of the state, you call exit on the state, and then whatever cleanup the method needs to do, whatever cleanup the state needs to do, it can do in that method there. And finally, depending on how you implement the class or how you implement your state machine, you might need a method or a pair of methods, has transition and next. So has transition returns true if the state wants to transition to a new state, right? And the next method returns the new state that it will transition to. So if has transition is true, next will actually return the new state object that the transition leads to. If has transition returns false, you have to decide on what you're going to return in next. In a language like C#, you could return null, or you might have a state object that represents no state, right? So there's a couple of ways that you can handle that. Right? So enter, do, exit, has transition, next. So that's what our state is going to look like. Okay, so we're going to look at this simple little problem here. That looks like, so that has that state machine representation there. So the idea here is that you've got a villager or villagers, sorry, living in a village, of course, right? And this is a resource, is simulating collecting resources of some kind. So here, one of the resources is wood, firewood. And so if you want your villager to go off and collect some firewood, the state machine representing the state of the villager at any time might look like this. Now, it might be considerably more complicated depending on how complicated your game is. So this particular example is chosen for its simplicity. Right? So the villager starts out in the village. Right? At some point, the villager either recognizes that, hey, we need some wood, or something tells the villager that wood is required. So there's this signal or a trigger that occurs that causes the villager to transition out of the in-village state, right? And so if some wood is required, that signals a transition of state. So the villager goes to a walking to tree state. Right? So if you think about what has to happen here, right? When you're in the village and you realize that you have to collect some wood, the villager has to do some work. It needs to compute, okay, where am I going to go collect the wood, right? So in other words, where is the nearest tree, or where is the tree to which I want from which I want to collect the wood? So there's some calculation that happens here, and then you transition out of the state, right? And now you're in the walking to the tree state. So this is the state that the villager is in when they're moving from the village to the tree. What do you do in the walking to tree state? Well, the villager moves, right? So you have to update their position every time. So you have to update their position in the do method. In the do method. Okay, so eventually the villager reaches the tree or gets close enough to the tree that you consider them for the purposes of your game. They've arrived at the tree, right? And so when you arrive at the tree, that signals another change in state, right? So you've gotten close enough to the tree, so the arrive at tree event occurs, and now you transition to a new state. So this is where the villager starts to chop down the tree, right? So what happens here? So while you're chopping the tree, some sort of animation is playing that shows the villager chopping down the tree. The interesting thing about this state here is that you probably want the animation to play for some amount of time, right? So in other words, you don't want the villager to show up at the tree and then suddenly start walking back to the village as though they had collected a bunch of wood, right? There's probably some animation there that plays for some number of seconds that simulates, that shows the villager chopping down or taking wood from the tree. Eventually, the villager collects enough wood from the tree, so their backpack is full, so that signals another transition in state, right? So now they go back walking to the village, right? When you transition to the state, so what happens while you're walking to the village? Well, the villager's position is changing. So now this is where you are doing, you're probably not doing path planning, but you're probably doing some sort of motion here, right? So you're walking back to the village. Eventually, you arrive at the village, at which point you can now drop off the wood, right? And now that you've dropped off the wood, you're back in the village. And so the cycle repeats, right? At least in this state diagram, the cycle repeats, right? So this is a very simple example of a state, of a finite state machine. It's simple because the transition, each state transitions to one state only. In a more realistic example, you will have multiple transitions out of each state. And modeling the problem quickly becomes much harder, even if you're using a state machine. So for assignment 2, you're going to take something that looks like this, and hopefully you're going to make it a little bit more complicated to solve the problem that you have to solve in assignment 2. That'll come out later today or tomorrow. All right, so the circles shown in pale blue, these are called the nodes. These are just the states, right? The arcs or the arrows between states are the transitions. So the nodes can have some sort of meaning associated with the actions, right? So for example, when you drop off wood, you probably want to increase the inventory of firewood in the village. Similarly, you're going to remove firewood from the villager's backpack, right? And so inside each one of these states, some sort of computation can occur that causes changes in your game. True of the transitions. And so the transitions can also have some sort of meaning in your game. Okay, so the transitions are triggered by something, right? By some sort of event that happens in the game world. Okay, so how are we going to implement this thing? So if we want to implement this using the state pattern, right, we're going to have a villager class that represents the villager, right? The villager is going to be the state machine, right? So or internally, they're going to have a state machine. So if you're using the gang of 4 state pattern, right, our villager, right, internally has a state object, right? So here I'm calling the state villager state. And so the state, that's the current state that the villager is in. There's some other information that every villager has, right? So here, we've chosen to have some attributes for the villager. So their speed, that's how fast they can walk, right? The backpack capacity, that's how big their backpack is, right? So it can hold 10 units of firewood. How much firewood is in the backpack right now? Well, there's 0 units of wood in the 0 units of firewood in their backpack right now. Right. And of course, depending on the problem you're trying to solve, you're going to have extra attributes here. The important part, though, is that you have a reference to a state, to the current state. Right. Now, this is Unity. So every mono behavior object has a start method. Right. So the start method is called when the villager object is created and then gets fired off. Right. So the first thing you do is you call start on the villager. Right. And so if you're representing the state of the villager as a state machine, you need to put the villager in its initial state. Right. And so here we're going to choose to put the villager in the in village state. So that's where they start out. Right. Now, when you enter a state, you have to remember every time you start in state, you want to call enter on the state. Notice I'm passing in this. So I'm passing in the villager to the state object so that the state object can ask the villager or can get information from the villager, like its speed or its capacity or its how much wood's in its backpack and so on and so on and so forth. Yeah. Yes, that's how this is going to work. So every state gets its own class, right? And the reason you want to put the reason why you want every state to have its own class is so that the logic for that state is isolated in one place. It's not all mingled up in one method somewhere. Right. Okay, so there's start. Every mono behavior has an update method, right? And so the update method, this deals with the transitions that the state machine might make, right? And it also deals with calling the do method for every for the villager, right? So if the state has a transition, then you know that the state wants to change, so it wants to change to a new state, right? When you change to a new state, right, the current state, you have to call its exit method, right? And so whatever cleanup the state object needs to do, it can now do, right? You then want to set the current state to the new state, right? And the state object knows what is the next state that it's transitioning to. So you call next on the state object, right? And then finally, you've got a new state, so you now want to enter that state, right? So now on the new state, you call the enter method, again, passing in the villager so that the state object can get information about the villager. There's another way to do this, so I'll explain in a second. Now, if we don't have a transition, then whatever state the object is in, we want the villager to be performing that action, right? And so the way you do that is you simply call the do method, passing in again the villager, so that the state has access to information that the villager has. Right? And there's update. Of course, if there's other stuff you could do in your update method, right? So whatever other game-related stuff you need to process in update, you can also put in here. Right? All right, any questions so far? So the key thing here in this pattern is that the villager has its own state, right? And now we can look at the state class itself. So for the state, it makes sense in this case to either make an interface, or in this particular case, it makes sense to make an abstract class. Right. So the reason we're making an abstract class here is because every villager state object has some information, right? It has data associated with it. So in particular, it knows its next state, right? And it knows whether or not there is a transition that's about to happen or that has occurred, right? So because every state object has its own state, notice the unfortunate choice of the word state, it makes sense to make an abstract class here rather than making an interface. If you make an interface, interfaces don't have data, right? So now you have to redeclare these fields in every one of your objects. We've decided that every state object should have an enter method, right? It should have a do method and it should have an exit method. These methods are all abstract because the subclasses need to implement these methods, right? There is no such thing as a generic villager state object, right? That's why it's abstract. Right? Notice here we're passing in the villager. So this is so that the state objects can access information that the villager has. Right? Alternatively, you can make a field up here called villager, and then when you create the state object in its constructor, you set the villager field, right? So the state object knows which villager to supply to. Right. So either have your methods take in the villager as a parameter, or make the villager a field of the class. Right. Either one works fine. Here I've decided to make it a parameter. Finally, there's has transition and next. And so many state objects can simply return has transition. Many state objects can simply return next for these methods, right? Some subclasses, though, will want to override these and change their behavior, and we'll see example of that shortly, right? So if they want to override them, you have to mark the method as virtual in C#. Right. All of this is new to me. I just learned this like 2 weeks ago. So if you guys probably know C# much better than I do. All right, so there's our villager state abstract class. Every one of our states will simply inherit from this class and specialize the enter, do, and exit methods. Some of them will specialize has transition. Maybe next too. We'll see. I don't remember anymore. Okay, so the in village state. So this is the state that every villager starts out in, right? It's the initial state. So you have to decide, okay, so what exactly is your villager going to be doing while they're in the village, right? So in a simple case, we're just going to have them stand around doing nothing. So typically what you're going to do in something like Unity, in the enter method, you're going to start the animation for the state, right? And so while they're in the village, they're going to start, stand around, or they might wander around at random or something like that, right? But on entering the state, typically you start the animation associated with the state. Whatever other initialization you need to do, you can do in the enter method, right? So if you need to set some of your fields, if your state has its own fields, you can set them in the enter method here. You could also set them in the constructor, right? But setting them in enter is fine as well. Okay, so while you're in the village, what do you want the villagers to do, right? And so, so in our particular in this example here, right, the villager is going to check, do we need some firewood? If the answer is yes, then we're going to find a tree to which to walk to, right? So now you have to search over the trees that are in your game, right? Exactly how you do that depends on how your game is set up, right? In Unity, you can loop over all of the game objects and look for the objects tagged with the tree, right? But here you have to do some calculation, right? I need to figure out, okay, so where am I going to walk to? And so that you're going to do that in the do method. Once you've decided that that firewood is required, now you're going to fire off a transition, right? So has transition returns true if the villager decides that firewood is needed, right? And if firewood is needed, the next method is going to return the walk to tree state, right? Okay, so on exit, what are you going to do? So it depends on what, you have a lot of flexibility on what you can do here. You can choose to do nothing here, right? As an example, I've inserted in, we're going to turn to the target tree direction. So we're going to start, we're not going to enter the animation where you're walking to the tree, but we're going to turn and look at the tree that we want to walk to, and then start the walking to animation when we enter the next state, right? You could put this in the enter method of the walk to tree state as well, right? It doesn't matter if you put it here or not. What is important here, though, is that you figure out what tree that you want to walk to, right? And so off we go, right? So there's your in-village state. That's what your in-village state class would look like, right? Exactly what code you put in here depends on how you've got things set up. Okay, so now we're going to go to the walking to tree state. So for the walking to tree state, on enter, you're going to start the walking animation. Right? What do you do while you're walking to the tree? Right? So this is one of the examples of a method where you're going to change the position of the villager. Right? And so while you're walking to the tree, you're going to check, has the villager reached the target tree? Right? If they haven't reached the target tree, you want to update their position using their speed. Right? So using their speed and the direction that they're facing in, right, you can update their new location, right? It's simply the current location plus the speed times the amount of time that elapses between frames. Right? So if you're not close enough to the tree, you're just going to keep on walking, right? So if you're not close enough to the tree, update the villager's position, right? Multiply its speed by the amount of time that's elapsed and move the villager by that distance, right? Eventually, now remember, do is being called for every frame, right? So eventually, the villager will reach the tree, hopefully, right? And so eventually, there's going to be another transition, right? And so the transition will occur when the villager reaches the target tree, right? And so this check part up here, check if the villager is close enough to the target tree, right? You can set a Boolean flag, has arrived, to true when you've gotten to the tree, right? So has transition will return true if has arrived is true, right? So that'd be one way to do it. There's other ways you can do this, right? If has transition returns true, then next can return the new state, right? The new state is going to be the chopping wood state, right? What do you do in exit? Well, it turns out you don't really have to do anything in the exit stage here, right? You might stop the walking animation, you might not, right? It depends on exactly how you want to do this, right? Here, we don't have to take any particular action, so exit can be empty. Okay, now we get to the chopping to wood state. So this is a slightly different state. So chopping to wood state, this is an example of a state where the transition out of the state is controlled by how much time has elapsed while you're in the state, right? So what you probably want to do here in your game is you want some sort of visual animation that shows the villager chopping the tree, right? So this animation is going to play for some amount of time, which I'm calling anim, right? So short for anime, right? So here you want to prevent transitions out of the state from occurring until at least that amount of time has occurred. So now we need some way to figure out how do I get time out of Unity, right? And now I have to check, has enough time elapsed, right? When enough time has elapsed, finally we can trigger the transition, right? You might be in a situation where one of your states requires a transition, forces a transition after some amount of time has elapsed, right? Here we want the transition to occur after some amount of time has elapsed, right? But you might be in a situation where after 1 second, something must happen, right? And so it's a similar idea. You're going to look at how much time has elapsed and then trigger the transition. Okay, so in the chopping the wood state, when you enter the state, you're going to start the chopping animation. Right? So what do you do while you're in the state? So while you're in the state, you're playing the animation, right? But you want the animation to last a certain amount of time, right? After a certain amount of time has passed, right? Now you can check, okay, have we collected enough firewood? Right? So if enough time has elapsed, go ahead and add some firewood to the villager's backpack. Right? Then, right, there's another piece to this, right? So you want to stop if the villager has collected enough wood. Right? So check if the villager's backpack is full. If it isn't full, right, you go back, you play the animation again, right? If enough time has elapsed, add some firewood to the villager's backpack, check if the villager's backpack is full, and so on and so on and so on. Right? So again, remember, do is being called repeatedly by the villager's update method. Right? Finally, on exit, the villager's got a full backpack. They want to go back to the village. So here we can say, well, let's turn and face the village. Right? Again, you can push this into the other state's entry method if you wanted to. Right? So when does has transition return true? Right? Returns true if the villager's backpack is full and enough time has elapsed. Now, because of the way we implemented do, you know that if the villager's backpack is full, enough time has elapsed, at least for the simple situation that we're in, right? You should think about exactly what's happening here. So I'm going to ask you in a little bit what happens when you slightly change the problem. The logic in here changes quite a bit. Right? So if there's a transition, you now want to transition to the walking back to the village state. Right? Which looks exactly like the walking to tree state. Right? So the chopping wood state looks something like this. Right? So there's our class. It's going to extend or inherit from villager. Inherit from villager state. Right? Now, we need to add a piece of information to the class. Right? We need to know when did we enter, or when did this state start. Right? So when did we enter this state? Nice. Oh wait, chopping wood, not wood. Right? So we need to record what time did we enter this state at, right? And so you can get the time from Unity using the time class, right? So big T time dot time gives you the current time in Unity, right? So we record the start time, right? We have no transition, right? Next is null, so we don't know what the next state is yet. Right? You're going to start your animation here, however you start your animation in Unity. Right? Do and exit, we're not showing them here. They're not that important, right? Do, though, is the method that's going to set has transition to true, or will eventually set it to true. Right now, remember what's going on here, right? The villager class is repeatedly asking, is repeatedly calling the do method. Sorry, is repeatedly call has transition, right? So has transition has to return false if enough time has not elapsed yet, right? And so here we're only going to return true if the current time minus the start time is greater than, here we're saying 5 seconds. This probably shouldn't be 5. There probably should be a variable up, a constant up here that says how much time the animation requires, right? But if the amount of time that has lapsed is greater than 5 seconds and there's a transition, then we can return true, right? If there's a transition, but the amount of time has the appropriate amount of time has not yet elapsed, then we're going to return false, right? So that forces or that causes has transition to never return true until a sufficient amount of time has passed, right? And so there is an example of a state that uses time as one of its criteria for determining if a transition can occur. Right? Walking back to the village is exactly the same as walking to a tree. Right? Instead of checking, are you close enough to the tree, you're going to check, are you close enough to the village? Right? And if you're not close enough to the village, you're going to update the position of the villager. Right? Again, using the villager's speed and the direction that they're facing in. Right? Once you get to the village, you're going to enter the dropping off wood state. Right? And just like the chopping wood state, dropping off the wood probably involves some sort of animation where the villager drops off some wood somewhere. Right? So again, you want to this state to not transition until a certain amount of time has elapsed. Right? So it's very similar to the chopping wood state. Right? So when you enter the animation, when you enter the dropping off wood state, you start the dropping off animation. Right? When enough time has elapsed, you empty the villager's backpack, add the firewood to the village's inventory. Right? Notice here, so there's something interesting here. So do has access, has access to the villager, right? Because you're passing in the villager as a parameter. It doesn't have access to the village. So there's an interesting problem here. So the question is how do you access the village, right? And so the answer is hopefully the villager knows where the village is, right? If the villager doesn't know where the village is, you have to do something like iterate over all the game objects and find the village object, right? But the state does need access to the game objects in the game. On exit, you don't have to do anything. On transition, you're going to go back to the village, right? So now the villager is back in the village, hanging around, waiting for the need for more firewood to occur, right? And so there is an example of setting up a state machine for a relatively simple problem. Okay, so these transitions, you can think of the transitions as having a guard, right? Some sort of Boolean condition, right? So when it's true, the transition is triggered, right? And so in all of these examples, there's some condition or combination of conditions that cause the transition to occur, right? If enough time has elapsed, right, then the transition occurs. Right? Walking to the village, right? If the villager is close enough to the village, then they've reached the village. Right? Chopping wood, if enough time has elapsed and the villager's backpack is full, right, trigger the transition. So you can think of all your transitions as having a guard. Where to go? Here, right? Just some condition that's true when you want to trigger a transition, right? So in our particular implementation, our transitions are not themselves objects, but there's nothing from stopping you from making your transition objects as well, right? Which you might need to do if your transitions also cause other stuff to happen. So you can certainly make the transitions themselves be objects. You have to decide on an interface for your transitions now. We don't need that in this particular case. Yes. So that's a good question. So the way that we're doing it here is in the update method in the villager, right? So that method is called every frame. So in a tip, depending on what you have your frame rate set to, 30 or 60 times a second or something like that, right? However fast your frame rate update is happening, right? And that's a good question because that's going to lead to the next slide, right? Shortly. Okay, so the next slide. Right. Okay, so is it the only way to implement a state machine? The answer is no. There's lots of different ways to implement a state machine. Um, so our villager class is itself, right? Itself, it implements the state machine, right? So remember what a state machine is. Every state machine has an initial state. So our start method inside the villager sets the initial state, right? In a state machine, there is the notion of the current state, right? The state machine can always be in one state, right? And so our current state in the villager class is just a field, right? And finally, you've got the transitions between states. So the transitions are handled in the update method of the villager class, right? And then the actual transition, so the states know how to transition to the next state. So that logic is implemented in the state classes themselves. So when you do it this way, your villager class itself essentially becomes, a part of it becomes an implementation of a state machine, which you might not want to do, right? Because now your villager class now has has at least two different responsibilities, right? It's a state machine, and it's also responsible for keeping track of all the information that a villager needs, right? And so you might say, well, look, we can take the state machine stuff and pull it out of the class, right? And we can implement our own state machine class. Then a villager can simply have a state machine object that takes care of all the state machine stuff. So you can certainly do it that way, right? So cook up your own state machine class, right? Your villager then gets an instance of the state machine. Um, the advantage of doing it this way is that you can reuse your state machine code, right? So now if you have a different type of object in your game, you can simply inherit from your state machine class and create a separate state machine for your other object. So that would be that's an alternative approach to implementing a state machine. Right. Okay, so the question that was asked previously was how often is this method being called, right? And the answer is, well, it's being called by update, and update runs for every frame, right? And so if you go back and look at the method and see what's happening here, where is update? Update. Okay, so remember 30 or 60 or however many times per frame, how many times per second your game is running at, right? Every time we're going to ask the state, do you have a transition, right? If the answer is no, we're going to go ahead and call the do method on the state object, right? And so this is a bit of a problem, right? It results in a lot of unnecessary work, especially if you know that state transitions are uncommon, right? So while the villager is walking to the tree, right, it's probably going to take 10 seconds or something to get to the tree. You don't really have to call update 60 times a second. You don't have to call the state object 60 times a second, like all the time, and ask it, is there a transition, right? The answer is probably almost always no. And so when you are regularly or synchronously calling or asking an object, has something happened, right? This is called polling. Right? This happens all over the place in engineering and computer science, right? Lots of devices poll, but it's kind of unnecessary in this case, right? There's no point in asking the state, have you transitioned, if you know the state is not transitioning very often. And so is there a better way to do this? The answer is yes, there is a better way to do this, right? So instead of the villager polling the state, right, you can put the responsibility onto the state itself, right? So you can have the state inform the villager that some transition has occurred. Right? If you want to do this, your villager needs a method that lets the state objects call the villager and tell it, hey, the state has changed, right? So add a method to your villager class, right, that the state objects can call when the states need to change when the states want to transition, right? It's not hard to do. Everything's the same here, right? You're still holding the state as one of your fields, right? In update now, you don't have to poll. You're not asking the states, hey, has something happened? You simply call do on the states, right? And you provide a method. In this case, I called it on transition. You can call it something else, right? On transition is going to be called by one of your state objects, and they're going to pass in the new state when they transition, right? So when the chopping to wood state needs to switch to go back to the village state, right? The chopping to wood state object calls the villager's on transition method, and passes in the walk back to village state object, right? Now here, you can simply exit the state, right? Set your state to the new state, right? And then enter the new state, right? And so that saves you from having to call, but having to pull or having to ask the state object over and over and over again, is there a transition, right? Instead, have the states tell the villager that a transition is required, right? Okay, so if you generalize this idea, this leads to something called the observer pattern, right? So the observer pattern is typically used when one object, so in our case, this would be the state, right, must inform multiple other objects, these are called the observers, that some event has occurred, right? So our observer in this case would be the villager. There's only one villager, so there's only one villager, right? The villager has its own state object. So you don't need to use the full-blown observer pattern in this case, right? But if you're in the situation where you've got one object and it needs to tell a whole bunch of other objects that something has happened, you probably want to look at the observer pattern. That's the Wikipedia page for that describes the observer pattern. There's a book that I mentioned in the previous class called Game Programming Patterns that also discusses the observer pattern here. So this is a worthwhile read if you're thinking about doing any more, if you're thinking of doing more game programming in the future. This book itself is it's a very easy read, and it's a very informative read. And it's free, so that's nice. Right. So this is an example of an event-driven state machine, right? State objects themselves are telling the subject, or the villager in this case, that something has happened and the villager needs to respond to that something. Okay, there are some problems with finite state machines. So in simple games, these things are fine. But as soon as your games have any amount of complexity in it, all sorts of the finite state machines start to run into the problems. So if we click on that link here, we go to the what's the catch part of the Game Programming Patterns book. And so we might as well do that now. Boom, it's right here. Okay. Okay, so the big problem with the finite state machine is that in a game, there's usually not just one thing happening, right? So in the last class, I used the example from this book, where you got a heroine or a character, a game character that can jump and duck and dive, right? And so you can create a little state machine that describes what happens when the character jumps and ducks and dives and things like that, right? Now, imagine that your character can be equipped with some piece of equipment, right? So they can have a gun or they cannot have a gun. They can have I don't know, some kind of tool, and they cannot have the tool, right? If you try to implement a state machine for this sort of thing, right, you now have a different state for all combinations of tools and guns and things and so on, right? So, and actions. So are they jumping and do they have a gun? That's one state. Are they jumping and no gun? That's another state. Are they jumping and they have a tool? That's another state, right? Are they jumping and they have a tool and a gun equipped? That's another state, right? So very quickly you end up with this state explosion, right? Lots and lots and lots and lots of state objects. Most of them are all the same, right? There's very little difference between most of these state objects, but now you've got all these objects all over the place, and it becomes very hard to deal with this complexity, right? So in these kinds of situations, you might end up using a separate state machine for each thing, right? So you have a jumping state machine for the action, so jump, duck, standing up, right? And then you have a separate state machine for what tools equipped, right? So do you have a gun or do you not have a gun, right? And things like that. So now you end up having two state machines, right? So here you've got your state, standing, jumping, ducking, right? And you have your equipment state, right? Do you have a gun? Do you not have a gun? Do you have an accident? Not have an accident? So on and so on and so forth, right? So now you end up having two different state machines, or n different state machines, depending on one for each of the n things that you need to represent. I guess I'll let you read the rest of this in your free time if you so choose. You can read a little bit more about some other extensions to state machines here, right? What time do we have here? 2:10, perfect. All right, and so that's all I want to say about state machines for this for this course, I think, for this course. So right, let's go back to the simple pattern here. All right. This thing here. Okay, this picture here, this is a very simple state machine. Right? So if you look at if you were paying attention to the logic that happens when we are in this state machine. So when we're chopping down a tree, so first of all, when you're walking to a tree, there's an assumption here that there is in fact a tree that you can chop down, right? And so more realistically, right, you might not be able to transition from the village to walk to a tree, right? You might need an intermediate state, right? Find a tree to chop down. And it could be the case that there isn't any tree to chop down, right? So in other words, you chop down all the trees in the neighborhood, there's nothing left to chop down, right? And so you have to, in a real game, you're going to have to account for stuff like that. Similarly, when you're chopping down a tree, remember you're trying to fill up the backpack, right? So it could be the case that you get to a tree that's almost completely chopped down already. So it doesn't have enough wood to actually fill up the backpack, right? And so now not only is there a transition to the backpack being full, but you've chopped down everything you can and your backpack's not full yet. So now what do you do? Right? So now you need another state, right? So here you might be into the find another tree state, right? Now I have to find another tree to go to in order to fill up the backpack, right? So there's another state here where you find another tree, then you have to go to the walking to the tree state, right? Then you go back to the chopping to the tree, and so on and so on and so forth, right? And so these state diagrams can become fairly complicated pretty quickly, even in simple games, right? So in assignment 2, you're going to start with something that looks like this, but you're going to have to modify it to include a little bit of the complexity that assignment 2 requires. Right? Assignment 2 is a resource gathering assignment, does involve resource gathering where the resources are finite. So you're going to have to insert extra nodes into this diagram to handle all of the special cases. Right? But the logic inside the states quickly becomes a little bit trickier to get right. So that's what you have to look forward to in assignment 2. Again, they'll come out today or tomorrow. It's almost done. All right, any questions about today's lecture material? All right, all done for today. I'll see you on Thursday.